Welcome everyone. This is our 89th live stream geometry. We have a couple people here with us now. So I see like 3 more people just joined. So today we're going to go over problems from the geometry problems and discussions Discord. So I know I've done that many weeks in a row. I've been wanting to go over the Iranian Geometry Olympiad problems, but I know they're not released yet. It's been a little while. So once those are released and they're public, then I will go over those instead. So if you'd like to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. All right, so I'm going to share my screen. And I know a couple countries had their clocks change today, and so some of them might come on later. But for now, I'll get started. So this problem looks like it looks like a simple problem, but I bet it's a little harder than it looks because it's a riddle, and riddle is the hardest. So basically you have a triangle within circle I, and you draw the feet of the angle bisectors. So a lot of these problems with the feet of the angle bisectors are actually really hard. I don't know if this will be another really hard one or if it's not quite as hard, but we'll see. So there's the end circle and I is the end center. And then we draw the feet of the angle bisectors, X, Y, and Z. I don't even, yeah, whenever I do this, like there's usually one of the feet of the angle bisectors that's like really close to the side of the triangle. But I'll try to make it so that it's not so bad. The closer you make it to being obtuse, the farther away these points are from the tangency. So that's usually what I try to do. So X, Y, and Z, I'm going to have to rename these. Oops. Let me see if I can get this point. I might have to move the diagram to get this. Just move it for now, and then I'll move it back a little bit. All right. So these are X, Y, and Z. And the end circle is tangent at B to BC. Let me hide these and close this. All right. So those are the 3 angle bisectors. And the perpendicular to YZ through A meets IB at point T. Okay, so O is the circumcenter of ABC. So let's draw that. Using the center tool. That looks pretty nice. So this is O. And then you draw this perpendicular to YZ, and you see where it meets IB. I'll draw the whole line, because often the whole line is useful. I don't think it meets on the circle, so I think that's just an illusion. Yeah, so for example, here it meets right there. I see someone put something in the chat, so I will check in just a second. So this is T. I'm also going to label this point because this point's often useful in problems like this. Hide this, and draw this. Draw this. All right. So the chat, this, yeah, it does have a nice statement. I agree. Yeah, it's not that complicated of a picture, but I don't know how hard or easy it is of a problem. So yeah, this is a right angle. Isn't there something with the Excenter where this is like, I forget what the theorem is.
Yeah. You take the Excenter, let's call it J, then OJ is perpendicular to YZ.
Okay. So that's probably helpful. So I'll draw that in.
It looks really good since we then can convert the problem into parallel lines, and everything like fits nicely.
Okay. So yeah, so this is where the Excenter touches BC at point G. And I'll draw those two rays. So AB and AC. And I could probably just do it like this. So this should be the Excenter where these intersect. So I'll have to shrink this a little bit in order to see it. I'll shrink it. It's hard to get it just the right amount. Like that for now. And let's draw this circle. So it's a well-known theorem that, so I'll just call this another letter, although, so is OK is perpendicular to YZ, right? I think that's the theorem, right?
Yeah, you can prove it using radical axis, but you have to draw the other two Excenters.
Okay.
I think I've solved the problem actually.
Oh, really? Wow.
Yeah. So you just need to add in the midpoint of BC.
Okay. Let me hide, just make it look nicer for a sec. So here's the midpoint. You call that M.
Okay, now OM is obviously perpendicular to BC. And another well-known theorem that AD is parallel to KM.
Yes.
So XD over XM is XA over XK.
Okay.
And let me just see. So also XD over XM is XT over XO, where we just take T as the intersection of OX and ID.
Okay, so we could call T prime this point, is what you're saying, right?
Yeah. And we want to show the parallel lines. So we want to show that AT prime is parallel to OK.
Okay.
And we have that T prime X over XO is XD over XM. And
which is AX over XK.
Yeah.
Because it's well known that AB is parallel to KM.
Exactly.
Okay. So yeah, we use two facts. So yeah, I'll just write it. I'll just start out saying those two well-known facts. So let M be the midpoint of BC. And let OX meet ID at T prime. And it looks like Ravi is joining us. All right. So I'll just say two well-known facts. KM is parallel to AD. So yeah, thanks for joining Ravi and Leia. KM is parallel to AD, that's well known. And also, the other well-known fact is that OK is perpendicular to YZ. All right, so maybe I'll prove those in the end after I write the rest of it up. So K is the Excenter. So I'm going to write that in the beginning. Let K be the A Excenter. Yeah, I like that we use both these facts in the problem. So then dx over xm is going to be ox over xt prime. And it's also ad over km. So yeah, so we have dx over xm equals ax over xk. And then we also have dx over xm is equal to ox or t prime x over xo. That means that ax over xk equals t prime x over xo, which means that at prime is parallel to OK. And that means that t prime equals t. Well, actually, that means at prime is perpendicular to yz, which implies t prime equals t. And then we have O, X, and T are collinear. Okay, so these two well-known facts sort of just crush it. Yeah, we could prove, yeah, let's prove those two facts. So I could label them as 1 and 2. So and 1 I think has a very simple proof. I forgot what it is.
You need to label the other two excenters.
Oh, or for the first fact, KM is parallel to AD.
Oh,
I think that
it's not that. Yeah, no, actually, the two excenter is for the second one.
the second one.
First one, I think I used harmonic bundle for it. I think
there's a very simple proof that doesn't even use harmonic bundle. So I think it's just if you draw the antipode of G, you just have to show there's a yeah. So if you draw the antipode of G, which you call G prime, then AD and G prime are collinear, and then it's just so
there's actually a way to prove like I use the two excenters for both of them. Yeah. And it's not really long, but
okay.
Like if you call J and L the other two excenters, we will have that triangle K KJL and DYZ are parallel, like they have corresponding parallel sides.
Sides, yeah.
And then we also have KM is the what's it called, the median line of triangle JKL, and DA is the median of DYZ. So KM must be parallel to DA.
Ah.
Yeah.
But I don't even know if you need some medians. That makes sense. I'll type that up. So let J and L be the B and C excenters. So then triangle JKL has all of its sides parallel to those of XYZ.
I think it's DYZ because we label the at point D.
Oh, sorry, DYZ. So wait, JKL, is that true? Like, because that's like not a symmetric statement then, right? So for JKL, the sides are all parallel.
Sorry. I mean, we got the label EF as actually we call them, I don't know what to call, but
points,
just
the points of tangency.
Yes,
Yeah.
The triangle with its vertices are
the in-touch triangle. I'll set to those of the in-touch. Yeah, I'm just too lazy. I could put the names of points, but let's see. Right. So once we know that, okay, so KM is the symmedian. KM is a symmedian of JKL. And DA is a symmedian in triangle. I'll just give it a triangle D. I'll just say DRS. And DA is a symmedian of triangle DRS. That means that AD is parallel to KM. So that's the first fact. And the second fact, how do you prove the second one? Sorry.
The second one, can you draw the two excenters? Because we're gonna need them.
Okay.
I believe.
All right.
I don't know if Stefan have any other proofs, but mine does use those two.
I've been lazy, so let's see. So the other ones, trying to draw it in like the simplest way possible. So these are the two excenters by the in-center excenter lemma. This would be L. Oh, it already was L. That's nice. And then this one would be J. Oops, sorry. Oh, but I called this J. I want the other one to be J. Okay. Let's call this something V. Running out of letters here. Okay. So these are the two X centers. I didn't draw the X circles, but should I draw the X circles too? So yeah, so we have this triangle here, JKL, and it passes through the, okay, since JKL has O as its 9-point circle. Okay. All right. So all right, I'm just going to write this out like this. KO passes through the center of IJL. Let me write this out. Okay. Okay, so I'll say proof of 2. So that's proof of 2. And this is proof of 1. All right, and yeah, I'll just leave this right here because I'm running out of room. But so triangle JKL, this is the 9-point circle because these are the 3 feet of the altitudes. So you have a triangle, you have the 9-point center, and it's well known that KO, so this is the line from a vertex to the 9-point center, and YZ is the radical axis. Okay, so ILJ, thanks for joining, Serdar. So we solved this problem. We're just thinking about 2 different lemmas that we used in it. So since triangle JKL, so, oh, it looks like Han just got kicked off, but now he is back on. So this is a vertex, the 9-point center of the X central triangle. It's well known that it passes through the center of IJL. Is that so the line from a vertex, the 9-point center, passes through the circumcenter of IJL, and it's easy to see that YZ. So that's a well-known fact.
It has an easy proof. It just like use one parallelogram thing
to prove it. Okay.
Because we know that the center of ILJ is the reflection of O with respect to LJ. So it's not really that hard to see.
Okay.
The reflection of JKL's circumcenter through LJ.
Okay, so, all right. And then YZ, probably by the radical, probably you could show the power of Y and Z with respect to both is the same. I'm guessing that's probably power, yeah, because this is cyclic. So like you have like AZ times ZB is IZ times ZL. And that shows, let me just think about this for 1 second. So yeah, IZ times ZL is the power of it with respect to IJL, and that would be AZ times ZB, which is the power with respect to O. So yeah, they both lie on the radical axis. Okay, so yeah, that makes sense. Interesting. So yeah, we've proven both these two well-known facts, and then after that, the problem follows pretty easily. All right. So, but yeah, before I move on to the next problem, I think there's a way to prove this first one without needing J and L. I think we can draw the antipode of G in this circle. And then basically, if we could show that then A, D, and G, so if G prime is the antipode of G, then A, D, and G prime are collinear. So if you look at triangle D, G, G prime, K is the midpoint of G, G prime, and M is the midpoint of this, that's well known. And so yeah, MK is going to be parallel to DG prime, and those are collinear. So yeah, that's a simple proof of, so yeah, this first fact can be proved pretty simply without needing J and L. But I like this idea. I like how it uses medians. It's, yeah, so interesting. All right, so thanks for sharing that solution. That's pretty cool that we solved it that quick. So yeah, for the people that just hopped on, we solved this very, very quick. We just spent most of the time writing up the solution. So let's move on to the next one, if my computer will let me. Can you guys see me trying to click this thing to, I'll do it this way. All right. So here is the next one. And it's, even though it's a riddle, I'm not sure how hard it is. So we'll see. We have a triangle ABC with circumcenter O. There were some very, very hard riddles, or they looked like very hard riddles, so I didn't do them. But if we get through everything fast, then maybe I could do some of them. They just have so many lines in the diagram. That's why I didn't choose them. But okay, so we have circumcenter O, and then we have a circle tangent to both AB, AC, and AB. So there can be more than one point for J. I mean, really, J can be any point on the angle bisector. So I'll draw that. So for the time being, we can call, I don't know, this J. And I'm guessing probably a homothety might let us, sometimes with problems like these, a homothety reduces it so that J could be any point on the bisector. So it could be that that's the case for this. So I'll see in just a second. So just to make it look nice, I'm gonna make E and F lie on the extensions. So so this would be E, this would be F, and we have to rename this as J. And no, actually, I'm not going to rename it yet, because here's why. I want to let B, E, and CF intersect at G. Oh, actually, I don't think you can just use a homothety. I think
what is the definition of D?
D, oh, yeah, it doesn't say what D is. That's very weird. Maybe, I wonder if this is really supposed to be D instead of G. Let's try that out. If that's true, yeah. I think this probably should be D. So let's check that out.
No, D is intersection of AG and BC.
Oh, really?
Yeah, that can be seen from the diagram on the server.
Okay, all right. So D is the intersection of AG and BC. Did they put that in the problem and I accidentally like deleted it, or they forgot to put that in the problem?
It is not
Doesn't
in the
matter.
problem.
Or what?
It is not in the statement, but just in the picture.
Okay, so I'll just write it here. So AG intersects BC at D. Okay, so now all of a sudden the problem looks a little bit harder than it did originally, but H is the orthocenter of BEF. So it's all the way up there. So I'm going to make it look a little better. And we want to show H, O, and J are collinear. If I make this a taller triangle, what do I make H? Yeah, the more slanted I make the triangle, the closer H is. And if I move J down, then H gets closer. So I think that looks okay. Something like that. All right, so let's make this look a little nicer. So yeah, this is the angle bisector. And I'm just going to draw up to points E and F. So like this, the F, CE, this and this. And this is the angle bisector. So I could draw the midpoint of this arc if I want. Call that M. And H is the orthocenter of DEF. So if we draw all of these, D is the orthocenter of HEF. If H is the orthocenter of DEF, D is the orthocenter of HEF. Okay. All right. Let's check that the problem's true. Yes. So obviously AFJE is cyclic, and I don't know if it's worth actually drawing the circle. Maybe not. Yeah, all we need to know is that J is on the bisector of ABC. So what happens when we move J around? Can we use Bricard's theorem somehow? We don't know. I doubt FBCE is cyclic. I think it's very unlikely. But yeah, we could probably use, let's see, Bricard's theorem. So we have EF. Oh, but ABGC is not cyclic. So we can't do that. Yeah, I feel like I want to use Ricard, but I can't. So, yeah, can we say anything about, is O, if you look at triangle HEF, D is the orthocenter. I was gonna say maybe O is like the Dumpty point or something. Let me draw this circumcircle of HEF. So it looks like Ryan just joined us. So thanks for joining. We're on our second problem. The first one was really, really nice, I feel like. So maybe, I don't think they'd be collinear with this point, but we could check. It's not, I think it's not impossible. So let's see. Yeah, those don't concur. So yeah, how do you draw the Dumpty point? I'm just wondering if O is the Dumpty point of this. Well, I guess then HOE would be tangent to HF, is that right? Yeah, it doesn't look tangent, so it's not a Dumpty point. This is tricky. And it looks like Roland is joining us. So, hey Roland, thanks for joining. So we're on our second problem. Yeah, this is an interesting one. There's a lot of flexibility because yeah, J can be wherever it wants on the angle bisector. Maybe Pappus's theorem might help. Or maybe we could somehow use Meckel's points or Meckel's theorem. So AFJE is cyclic. I feel like I'd like to use that if possible. Not only is it cyclic, it's harmonic. So maybe there's some point that we can project through. I'm going to delete this for now. Well, actually, let's see if we can use this circle at all. So D is the orthocenter of HEF. How do we use that fact? So if I reflect it, okay, so HD is parallel to AJ. That took me a while to realize, but that's true. So HD is parallel to AJ, and maybe we could use that I is the midpoint of DK. That might be a good way to use it. And also, I wonder what the circumcenter of this circle is. Interesting. So, so we know the circumcenter of this is going to lie on AJ by symmetry. And does LM equal MN? I think that's probably a coincidence. I doubt that would be true in general. Yeah, that's not true. But HD should be 2LN. So DI equals IK. Not sure how to use that fact. And it looks like we now have Boomy joining. Hey, Boomy. So, yeah, Boomy, we're on our second problem. I'm starting to wonder how useful this circle is. Unless we can show that like K lies on this circle, but no, I don't think it does. So can we project through some other point? Let's see. Oh, are J, I, and that point collinear? Or is that a coincidence or concurrent? Yeah, it looks like it's true. Interesting. That's very random. So Ji. Okay, so let's hide this circle because maybe it's not as useful. Well, we need it for point K, but it looks like Ji and this point lie on a line. I don't know why yet. One sec, I'll be right back. All right, back.
Proof for the concurrency, the point B.
Oh yeah.
We want to prove that F over PE equals to Fi over IE. We now define P as intersection of two circles, and we want to prove that J, P are collinear. Now we know that BF over PE equals to BF over CE. So we want to prove that DF over CE equals to Fi over IE. And this is true because DI is angle bisector of BIC, and two triangles BFI and IEC are similar.
Okay, so BFI and I. Okay, so sorry. But let me. Okay, so you're trying to prove that PI and J are collinear, right?
Yeah.
And you're trying to do that by showing. Did you say like PF over PE is JF over
Fi over IE, because we want to prove that PJ is angle bisector.
Okay, so we want to show PF over PE is IF over IE.
Yeah.
And how do we get PF over PE?
Because of spiral similarity, PF over PE equals to BF over CE.
BF over CE. Okay.
Yeah, and from DI is angle bisector of BIC, we deduce that BFI and IEC are similar.
Because ID is an angle bisector of BIC.
Yeah, that's projective. That's a well-known fact. If you intersect BC with EF, you can see it.
That is harmonic. Okay. Okay, so that proves that PI and J are collinear.
Also, MD and P are collinear.
Okay. Very interesting. Did you prove it, or it's something you noticed?
From Serdar's proof, we can also do this.
Okay.
Also by Apollonius circle.
Oh yeah, because triangle PB over PC is also BF over CE, so you kind of get the same proof. And then BDF is similar, yeah. Okay, so that's some good progress. So L is the center.
AO, TJ, and circumcircle of ABC are concurrent.
Say those again.
If you intersect JP with circumcircle of ABC, it's the antipode of A.
Okay.
Yes.
So this is the antipode.
Yeah, because AJ is diameter.
Okay.
Can you check? No, okay, it's not true.
Oh yeah, at first I thought this passed through L. I was like, what? That doesn't make sense. But yeah, it doesn't. That's just the way the diagram was drawn. Made it look like it.
RH2J cyclic.
What?
AHQJ.
AH and QJ. Okay.
Are they cyclic?
Oh, are they cyclic? No. So APQ is 90 degrees, which means APJ is 90 degrees. Yeah, which is true because, yeah, it lies on that circle. Maybe I should get, I don't know. Do you think I should get rid of this circle?
Yeah.
All right. So I guess I could just use that HD as 2. Well, yeah, how should I use it? That's the orthocenter. Maybe I could use something with like anti-Steiner points because we have a lot of lines through the orthocenter here. Let's see. I wonder if O and M are isogonal conjugates. And H, yeah. Oops. So OFH, EFD. Oh no, that looks like a much smaller angle. Maybe O and G. But even still, I think it's. Now I can try Q. Very, very close, but they're not quite the same. But yeah, we have to use that D as the orthocenter of HEF. And if I don't draw the circumcircle, I'm not 100% sure how else to do it. Maybe there's something special about, I'll just draw the center of the circumcenter of HEF, like point L. Because it lies on AJ, we know that. Okay, or yeah, we call it K. So K is the circumcenter of HEF. And HD is 2KN. Oh, you know what? I wonder if there's something special about the antipode of H. Because this is the other way we could use that D as the orthocenter. To take the antipode of H and then D, N, and H prime are collinear. I like trying to use that fact. Maybe a spiral similarity takes like one to the other. I wonder if P is like the Q point of well, no, that would mean angle HPD is 90, which I don't think is true. Yeah. Are these parallel, these two? Let's see. Just move stuff around for a sec. I don't think so. Let's see. No. So
What
AH,
did you guys call point K?
K is the circumcenter of HF H prime E. Or K is the circumcenter of HFE. And we know it has to lie on this, AJ. So yeah, triangles AKH and JKH prime are congruent, I think. Yes. So AHJ, H prime is a parallelogram. And yeah, we have a lot of, so FJ and FH are isogonal, and EH prime and EA are isogonal.
Actually, if you call T is the orthocenter of AEF, then HT is perpendicular to BC. I don't know if it helps.
Okay, so the orthocenter of AEF.
And yeah, and if you connect that point to H, then that line will be perpendicular to BC.
Okay, so T is the T is so close to point K, unfortunately. Let's see if I can make it a little farther away. So T is the orthocenter of AEF, you said?
Yes.
All right. Then you said that T, what did you say was true then?
TH is perpendicular to BC.
Are you sure? Because we know K. So TH you're saying is perpendicular to BC. Okay, interesting.
Yeah, and I can prove it. So if you need it, I will use it later.
Okay. All right, I will do it something like this. It's getting a little messy, I know, but yeah, it's hard to draw a good diagram here. Maybe I'll draw a diagram more like, it's driving me crazy. Yeah, I want to use that these are isogonal and these are isogonal, although I don't know if it's that easy. I wonder if, let's see. I wonder if there's some other thing that's like isogonal. So So T is the reflection of J over EF. And H is the orthocenter of DEF. So HT is perpendicular to BC, and I don't think OM and H prime are, no, I don't think it looks true there, but I don't think that's actually true. Yeah. So I'll be right back. All right. So what if I take AFJE and I project through I onto that circle? Then we'd have a harmonic quadrilateral. So that means EFPL is harmonic. Oops. So if EFPL is harmonic, then LN and LP are isogonal. So we have a lot of isogonals. Let's see. Let's see. If I draw this, I could get rid of this point H prime. I just don't know how I'd use it. This is the orthocenter then. I kind of like that idea because then we have lots of isogonals, right? So FH prime and FJ, or FJ and FH are isogonal, and then this and this are isogonal, and then PL and what is it? PL, LP, and LN are isogonal. Isn't there some theorem with like isogonal quadrilaterals or something?
What are isogonal quadrilaterals?
So we have like, I don't
There is a
know.
theorem about isogonal conjugates in a quadrilateral, but I don't know if you mean about that.
Yeah. What is that theorem?
So if you take quadrilateral ABCD and point P, then it has an isogonal conjugate in that quadrilateral if and only if, so here in your diagram, angle RWV plus SWU is 180 degrees.
Okay. So if those two add up to 180, then this point has an isogonal conjugate.
Yeah.
Okay. So if that's true, then point H, I think point H should have an isogonal conjugate in quadrilateral AFJE. And it should be, so what if I let EJ meet FH prime? Sorry, let me just move this here so I can see it better. Then I think H and R might be isogonal conjugates in AFJE.
Are you sure H has isogonal conjugate?
Or so I guess in the quadrilateral AFJE meets the oh wait, actually never mind. Let's see. JR. Yeah, no, I'm just getting confused here. So yeah, this should be the reflection of P over AJ. But yeah, that doesn't do much. try this. So yeah, Rn, so AR equals Kn. Do I even have the center of, there's a lot of points here. So S, is FJ parallel to AP? No. So HT you can prove is perpendicular to BC. So the angle THI is the angle between BC and EF. Yeah, there's so much stuff here. Yeah, we can spend like another 10 minutes or so on this. And then we'll see if we want to move on to the next one. So yeah, so D is the orthocenter of HEF, and we have a lot of lines through the orthocenter. That's really the key. We have to use that D is the orthocenter of HEF, and how to do that, I don't know if H prime is a good way to do it, or if there's a better way. But if Kahn can prove that HT is perpendicular to BC, then yeah, we probably don't need H prime. We could probably use that fact. So So yeah, if you can prove that HT is perpendicular to BC, then we don't really need H prime. Because we can basically say T is a reflection of J over point N. And then we could define H. We could define H to be the intersection of IB with a perpendicular from T to BC. And then K, I don't even remember what K is. I think K is the midpoint of AJ. Well, so OK is parallel to PJ. Maybe that's helpful. And OM is parallel to TH.
Maybe we can add in the midpoint of BC.
Yes.
And then we need to prove parallel lines.
So what do we need to show as parallel?
HT is parallel to OS.
Oh, but Khan said he's already proven that.
Yeah, but if we define H as intersection of OJ and DI.
OJ. Oh, so proving it like that. Okay. So we could call that H prime. Yeah, I kind of like that. So yeah, maybe we could take some stuff out of this picture. I'm going to get rid of point L. I like that idea, but yeah, I don't know how far that's going to go. So you get rid of that. So we have ID intersect yeah, so we know that, yeah, this is an angle bisector right here. ID and OJ. And then we want to show that HT is parallel to OM. I kind of like that because that's the same as showing, so we want to show that JT over JH prime equals JM over JO. And we know that JT is 2JN. Oh, and MQ is parallel to EF. So yeah, that actually might be really helpful. Because we have, so JT is 2JN, and JN over JM is JI over JQ. Yeah, I just don't know. Yeah, how do you get JO over JH prime? So yeah, I shouldn't call. So basically, let's see what's a letter. Just call it Z. I wonder if ZI is parallel to AQ. Yes, and I think it's equivalent. So if we let Z be the midpoint of H prime J, then we want to show ZI is parallel to AO. Yeah, I feel like I'm maybe going in circles here, but yeah, we want to show ZI is parallel to AO. Okay.
Zn is perpendicular to BC. That is obvious, but looks useful.
Zn. Okay.
No, actually, that is equivalent, I think.
Equivalent to the problem?
Yeah, equivalent. Just because you have the midline of TJH prime.
Okay. I think we're close. Just a matter of my brain is hurting. But yeah, I do think we're very close. Yeah, I wonder if we need point P for all this. Like, and if we need the circle even. I'm gonna hide a bunch of stuff because I feel like it'll just make it easier in my brain. Well, yeah. he was interesting, but maybe we could just do with less. So this is a rhombus right here. And yeah, do we really need point Q? As long as we have AO, I'm going to get rid of point Q. And what was R? I don't even remember anymore. Let me get rid of that. So yeah, let's define things like this. And so we have JO intersects ID at H prime, and T is the orthocenter of AEF. And then we want to show that those are perpendicular. And that happens to be the same as showing that ZN is perpendicular. So yeah, we can hide a lot here. We just want to show ZN is perpendicular to BC. So yeah, we don't need T then. I don't think we need K. I think we need that. Okay, so we want to show Zn. Z is the midpoint of H prime J. And we want to show Zn is perpendicular to BC. So Nm times Ma is the power of n. Maybe we could even show NB squared minus NC squared as ZB squared minus CC squared. Not sure. So it's probably worth, I don't know why I haven't done this, but so AFJE is going to be similar to A M prime B M C. And we want to show H prime N. So N and S are corresponding points. And BC corresponds to EF. Yeah, let's draw this circle again. So have these similar figures. Now I'm wondering if we really did want P. Because yeah, then we'd have a lot of spiral similarities. And so BC corresponds to EF and ZN. So yeah, I'm trying to think, what is NS? Like yeah, that spiral similarity, is there anything else that it does? Where does it take point I to? Does it take point I to point D? I think, yeah, we said it did. So Z, does it take H prime to some point? So it takes I to D, and we let ID so what does that mean? MID. Yeah, we have a lot of corresponding things. Yeah, I think we really want to draw the center of this because L is the center. Then that takes O to L. And we have I'm just getting confused. All right, another 10 minutes, and then I think I'll move on to the next problem. So JO, what can we say about JO? So a spiral similarity about H, it takes MO to JL. So the angle between everything is pretty much angle AJO. Everything in the spiral similarity. Just need one more idea here. All right, you guys want to move on to the next one?
Let's stay for more like 10 or 15 minutes.
Okay, I'll do it for 10 minutes. J. Yeah, let's call this P instead, so we don't get confused. So we want to show JN over JL. JN over JM is JZ over JO. But we have JN over JA, it's MS. We can calculate that ratio easily. It's just yeah, what similar triangles can we find? So I wonder if this angle here, I wonder if we can say something about this angle. $12.24. Is there any other angle equal to that? Well, angle OJA is obviously equal to that. And let's see. Moving points. What if we draw this midpoint? I mean, it's the same as showing that NZ and H are collinear. Well, not really, actually. I don't even remember, how is point I defined? Oh yeah, it's just the perpendicular from B to E. So yeah, I think we really want to use that IB bisects angle BIC. I feel like that is something that we haven't used enough. So IB over IC. Yeah, so Serdar mentioned that. Ooh. My brain hurts.
Sorry, Stefan, I didn't read the chat. What moving points though?
Oh, it's a certain technique that you can use to solve problems where it's like, for some problems, if you can prove it in like 3 cases, then you can prove it for like all cases. So it's like if we could prove it where J equals M and then j equals another point, and then j equals a third point, then sometimes there's some trick where you can show that if you show it for 3, then you've shown it for everything.
Yeah, this, for example, this is trivial for J is the Excenter.
Okay.
So if we could like do these moving points and 3 are enough, then we would probably be able to solve the problem. But I don't know how that method actually works.
So maybe if j is the Excenter, and then j equals m, and then j is the Excenter, or something like that. Or maybe like j is the point at infinity, then that might do it. All right. All right, I think I'm going to move on to the next problem. If you end up still wanting to work on this on your own and you find a solution, yeah, you can tell me before the end of the session and I'll write it up. But as far as just making the video, I think I want to move on to another problem. So these should be a little bit easier because they're, or this one's a middle riddle. So